Good morning.
Hello, good morning.
Because now we are going live from Chicago, and it's Tuesday morning, and life is beautiful outside, but here we are stuck inside. Complex integration. So, so far, no big deal. I told you that I can define differentiation in two-dimensional plane, and the trick was Cauchy-Riemann relations that says that if the function is really funky, satisfies these relations between real and imaginary parts of it, then it's called holomorphic. And derivative has a property that it doesn't matter how we approach the point, it's independent of direction, I always get the same answer. So you get used to this, so what? Now we get a payback. The inverse operation of derivation is integration. Because the derivatives don't depend how I approach a point, the integrations won't care on what line I take in complex plane, I will get the same answer. And this now gives insanely many, unexpected beautiful results that made people in the beginning of 19th century be as happy as quantum mechanicians were happy in the beginning of 20th century, because they could compute infinitely many integrals that nobody could do before. It was just a beautiful thing. So the real thing about complex analysis happens this week and next, which is complex integration, not derivation. So what I'll do is, it's lots of stuff. I have to derive stuff. So I'll state the results now. That's what I expect you to take home and remember when you're designing a better airfoil. Here are the basic facts that I want you to remember. First thing is called Cauchy theorem. Cauchy theorem says that if I take any curve in a complex plane, A, for misspelling of curve, or German word Kurve, that any integral, no matter what it is simply zero. Amazing. Out of this comes what people might call deformation theorem. So if I take an integration along curve K from initial point to final point, or I take an integral along curve L from these 2 points, or I take anything in between them, I get the same result. So I have path independence of complex integration. Now this is direct consequence of path independence or angle of approach independence of complex differentiation. That's just the inverse statement, but it's so much more powerful. And out of it comes Cauchy theorem, which says that if I take any curve, no matter how crazy, so here is some crazy curve, can cross itself, doesn't matter, can go around, can do funny stuff. But, direction is important, so I have to indicate direction by little arrows. And as long as I'm going through neighborhoods which are holomorphic, meaning derivative is defined, and I avoid this area here, which is crazy, non-singular, not holomorphic, I always get the integral to be zero. Pretty cool. Now we use this theorem plus deformation in 2 ways, and that's called secret of contour integration. If I have some contour in a complex plane, meaning I follow any curve in a complex plane, then I'll show that I can deform this curve into two disconnected curves. So this is integration around K. We will show that this is sum of integrals around two little curves. And then we'll find tricks to compute these separate integrals, and we will do some amazing things. And what I'm supposed to avoid are singular points or singular regions. So that's what these little dots mean. They could be larger than a point. Simplest case, they'll be just a point. Now, more generally, I can take some complicated route through the world in a complex plane, going around, always avoiding singular regions. So I roller skate or whatever, always avoiding singular regions. And this contour integration theorem will say that we have to look at singularities that are contained within a contour integration. So for example, this one is outside, we forget it. This one is outside, we forget it. Now these guys we cannot forget. And we can replace this big contour integral with the little integrals around individual, so some of the individual ones. And each one of them, we do our integration where we develop special tricks how to do this integration. And now associated with it is a number which is positive or negative integer. So this is an integer which depends on the contour. This is contour. And it depends on singularity. This integer depends, it's +1 if we go around a given singularity only once in a usual right-hand definition of going counterclockwise. It's -1 if our contour goes the other way. And if it goes around 3 times, then it's +3 or -3, depending on the sign. So that's what I want you to remember forever from this course, whenever you have to look at integrals. And remember that Hadamard said, the line that connects two truths in a real domain goes through the complex plane. And that's very true for these integrals. And I'll remark, all these orientations, etc., this is all wedded to a two-dimensional plane. If you're in 3 dimensions, we wouldn't have this notion. We could deform curves in some weird way without having orientation. And that's one of the reasons that all this beautiful magic we learn in complex analysis doesn't carry to higher dimensional spaces. Later, when you learn, if you learn some fancy geometry, there'll be things called indices, etc., that can be defined in higher dimensions, but they're much harder to deal with. So let's now define the contour integral. I just stated the facts, but how do we define it? So we have a situation where we go from initial point zi for initial along some contour and end up at a final point. So let's call this contour K. And now what happens to its image, we'll get some kind of continuous line in the function space, whatever the function is. So this point will map here final point will map here, and every point in between will trace out a curve. As I move on this curve, I'll get some other curve, which will do whatever it does. But we'll end up at the final point. So that's the image of K moving in the original map. Now, how do we do integrals? Especially if you're doing it computers, but also that's how Euler sort of went first. Whenever you have a curve on which you're integrating, let me use some innocent color. So I start here and I move around. The way we do it is we discretize, which means we replace this piece of curve by an interval, which we'll call delta 1. It's a little complex vector 1. This one by interval delta 2, and so on. And eventually there'll be a delta n. So these intervals are little complex vectors, very short, and in the limit of n going to infinity, intervals are supposed to all shrink to 0. So you make them of comparable size, magnitude. And then the integral is defined as sum over values of the function on discrete points, this point, this point, this point, this point, multiply by the interval, the infinitesimal change. And you take a limit of infinitely many points. Now what's happening on the right-hand side is that the function is taking different values and you're having jumps in a complex plane on discrete points. And that's what's happening to this function. So you just need to know it on discrete points. So that's the usual definition. This doesn't actually depend on complex plane. This is just the usual definition of integral on a curve in any dimension. Even if we do this in fluid dynamics in 100,000 or million dimensions, the state is a curve in that very high dimension space, and we integrate, and that's called integrating Navier-Stokes equations. Here it's just 2 dimensions, it's not specific to complex stuff. And you look at this definition and you realize the usual rules of integration apply. So if you multiply the function by a constant, C, that's same as C defining the integral. If you take 2 functions on a curve, you can integrate separately. So it's additive, distributive, usual way. And here is a particularly useful property. If I first go on a curve K up to this point, and then I continue on a curve L up to this point, then the integral, because it's a sum of little steps, is additive. So I can add the integral here to the integral there. You will use that a lot. And the other thing that you see from the definition, if I change the orientation of the little steps, so they don't go this way, but they go that way, that's the same as retracing the function, starting final point and going back to initial point. And that's a minus of the original integration. That's same as, from one-dimensional integrals. Another thing that you know from one-dimensional integrals, which is very useful, is the notion of parametric integration, which means instead of looking at z as your variable, you define z to be a function of some parameter. For example, you're moving and you look at your watch and you're at different points and different times. So that's little t here. And if you change the variables, you have to change z into the function of t, and that gives you this derivative here in changing a variable. And f is now a function of t. And now you say I start at time, 9:30, and I'm supposed to finish by 10:15. We know that we can always write z as real and imaginary parts. So this function of my clock time has a function of t real part and imaginary part, you know that. And we know that we can also always write w, this function, as real function plus I imaginary function parameterized by t. Now, taking this derivative, the dot will mean derivative with respect to time or parameter of the my integration. Doesn't have to be time, but some parameter. Could be the length along the curve in Euclidean units or something. So that gives me dot here and dot here. And now I multiply all these terms, I get 4 terms. So for example, u times x dot is this one, v times this guy has i's in it, so there's a minus sign vy dot. Then, there are 2 cross terms, so there is u times y dot is a cross term, and v times x dot is a cross term. And I get this parametric integral, a complex plane, to be just 2 ordinary kitchen variety integrals. This is a real function minus real function, and this is I multiplying 2 ordinary integrals. So these integrals are no big deal. They're really integrals that you're familiar with. They just happen to be in a complex plane. To get some intuition, let's do a few examples. And this one you might not get immediately in the lecture, but I will not answer questions about it because you can think about it later. So here are a few very simple counters. So for example, let's start at 0, move on a real line to 1, and then go in imaginary direction until we reach 1 plus I. This is the point in a complex plane. So this integral, I'm integrating along real part. And I know that integral from 0 to 1 of x dx is 1/2. Because integral is 1 square for 1/2, etc. But then and this one you'll have to think about, then I take over this way, and that's an integral over this quantity times imaginary part. So this part is just 1, and this part is y squared, so I'll get an integral 1/2, I add them up, and I get 1 plus I. So that's what this integral is. But I can decide, be courageous, just go straight for it, right-hand corners. That's parameterized by final point times t. So when t is 0, this is 0. When t is 1, this is the final point. So that's what I'm integrating over. Then, I have to take derivative of that part. That's what this is. That's d function over dt times dt. And, that's easy to integrate. This part is I plus 1, and this part will give me 1/2 minus, etc. And I get 1. And I notice, I took 2 counters, I get 2 different answers. So the thing is not so simple. You have to think about it. about complex integration, what makes it work. Here is another one which we'll use a lot. Let's run on a circle around the origin, one time around the circle. And take the radius circle to be 1. Then the function is just real part is 1 and imaginary part is it, and I forgot why I decided to call this minus it, but I run around once. So this is my derivative of the function. Now I take the derivative, I get an I down times dt. These two guys cancel. So I'm running from 0 to 2 pi dt. I know how to integrate constant function or 2 pi, but I pick up an I here. So this circle integral is 2 pi I. We'll find it very useful. There is a bunch of this kind of integral which you can do, but here is the most important. Here we are in complex plane, and we take a contour going a contour rotation. And I would like to evaluate the integral going on a loop. So this integration always means we're going on a curve that closes onto itself. And the function I want to study is just inverse of z, tc. And this is a nice function, holomorphic, except at z equals 0, it's not holomorphic, it's singular. Because it just runs off to infinity. So we have a singularity at the origin. What do? We add any place a little side contour that goes this way and goes back. Now, I draw them as separate, but this is actually, it goes back along the same route. So it means that this way I get plus, this way minus. So this part cancels itself. Now this is new, it goes that way. So now what I do is I stick a little contour on top of this one that goes the opposite way. So now I've added two little things, and let's call this one C2, this one C1. So I'm using this deformation theorem, saying I can just deform contour any way I want. And I've deformed it in such a way that I've done something that's always illegal. I've gone through a region while I'm continuously deforming, which is singular. I'm not allowed to do that. I'm only allowed to go through holomorphic neighborhoods while I'm deforming it. So to make up for this, I cancel exactly the violating part. So now we have that our integral over contour C1, well, the original contour. Now C1 is the guy that does all this weird stuff. So integral over C is integral of C1, so 1 with the detour, plus integral of C2 which was inserted here to just circle the origin. Now this guy, when you look at it, it's a thing that goes around, and I can deform it. I can separate these points, I can move it around, and I realize this vanishes. So we replaced a big contour C by this small contour that's just sitting close to the origin. So now I'm allowed to make this a circle. I'm looking at the integral of dz around the origin of the 1 over z. That's the function. So let's make z rho its magnitude e to the I theta. And now I've actually just done this integral. I'm going around singularity at the origin. And when I change my parameters, when I parameterize this in terms of rho and theta, rho is not changing. So I pick up 1 over rho times e to the I theta. That's 1 over z. And dz becomes rho I, because I take a derivative with respect to theta d theta. These two guys cancel. And I've, of course, forgotten to write e to the I theta here. And these two guys cancel. And I'm just doing the integral I just did a moment ago, 0 from 2 pi delta theta, but there is an I. Our final result, integral on any contour C of 1 over z dz equals 2 pi I. Magic. That's well, we're in complex plane doing something going on, so you can see we're kind of circling, but qualitatively circling. But we get that any integral around any that contains a function which is called a simple pole, and this is not ethnic slur or anything. Pole is just a value where a complex function diverges like 1 over z. That's a technical term. Any one of them will give me 2 pi I. And now I can go back to facts of life as I stated it originally. This is the only thing you need to do general complex integration. If you have simple poles, then you will just sum up the poles which are enclosed by the counter, ignore the rest, and that gives you a formula. There'll be just a bunch of 2 pi i's. The next thing that I'll have to show is that if you say, well, it's a simple pole, what happens if I integrate over 1 over z squared or 1 over z to the 5th? That'll be something really crazy, because that'll really blow up at the origin because it's a higher power of a small number. The magic of complex integration, all of those guys will be 0. Only the simple pole matters.
I have a question, just to make sure I understand it correctly. If we were to take the integral in the counterclockwise direction, then we would add up minus 2i for each enclosed.
Yeah, so I didn't make it very clear in this example, but I even forgot to put the arrow here. So this rule is for the contour which counter that's going counterclockwise, if I change the direction of the counter, then dz changes sign, this little interval, the little vectors, and they all flip. So I'll get minus 2 pi. So that's why in the final answer, you have this, mu, and that can be plus or minus 1 if I go around once. But, I'm also allowed to go many times around, and then I'll pick up 1 every time I go around. So they'll just add up. So mu can be positive or negative. Integer is positive for anti-clockwise, negative for clockwise. It's 1 if I go around once, and it's 7 if I go around 7 times. And that happens. Thanks, Juliet. Thank you for speaking up. I will, the silence kills me. Next question.